Hello there, my name is Roman Sonnleitner, and my focus for nearly 20 years at voestalpine has been on electrical steel. Electrical steel is supplied as a steel strip with special properties for electric motor and generator applications. It is used in machines that convert electricity into motion and conversely movement into electricity. But why are the properties of electrical steel so important? Let's take a closer look. Take, for example, an electric motor, a skillfully engineered device that creates magnetic fields between a moving component, the rotor, and a stationary component, the stator. These magnetic fields are often generated and controlled by electromagnets, the production of which would never be possible without electrical steel. This is a cold-rolled steel strip made of iron-silicon alloys, but with very special properties. High-quality electrical steel made by voestalpine can contribute significantly to more power and efficiency, which leads to lower power consumption in electric motors. But why is that? What are the properties of electrical steel? Let's begin with the most important technical terms: permeability and magnetic flux density. These values should be as high as possible because they describe the strength of the electromagnet. And core losses that occur when an electromagnet reverses its polarity, meaning when the magnetic field changes direction, and should be as low as possible. Let's look more closely at permeability and magnetic flux density. In the voestalpine steel tutorial that focuses on magnetism, we learned that the magnetic field in an electromagnet is generated by a current-carrying coil, and that the strength of the magnetic field, represented by the number of field lines, depends heavily on the material in the coil. If only air is in the coil, there is only a small number of field lines. But if a core made of electrical steel is in the coil, the number of field lines increases sharply. So it makes sense to use a defined technical term, magnetic flux density B. Magnetic flux density B indicates how many magnetic field lines are in the coil. The following formula is used as a description. B is mu times H, meaning that the higher the magnetic field H of the coil, the higher the flux density B is, caused by the current through the windings, and multiplied by a gain factor mu of the material inside the coil. The formula contains a new term, mu permeability. Generally speaking, permeability mu is a measure of a material's ability to amplify magnetic fields. This means that our higher mu electrical steel amplifies the magnetic field many times over. Permeability is calculated using the vacuum permeability constant mu0 and the value of the respective material, which is referred to as mu-r. Air has a relative permeability of close to 1, while that of ferromagnetic substances such as iron, cobalt, and nickel is in the range of several thousand. These elements can be used to generate far stronger magnetic fields. Vacuum permeability mu0 has a very small value. For the sake of completeness, I would like to speak briefly about magnetic polarization P, because it is often used as a material parameter. Magnetic polarization P refers to the difference between the flux density B in the respective material minus the flux density in the vacuum at the same magnetic field strength H. But the flux density in a vacuum is only a very small value, and so the value of B is almost identical to P. Let us now look at the second deciding factor in electrical steel, core loss. The movement of an electric motor is caused by continual changes in the direction of the magnetic fields. Let's look at what happens in the electrical steel. We can see it this way. There are many small rod magnets in the iron core of electrical strip. In my explanations, I refer to them as dipoles. First, I place the iron core into a coil, and as long as no current is flowing, the dipoles do not have a common orientation. When current flows, however, they gradually align themselves and amplify the magnetic field. When the direction of the current changes, they align in opposite directions, and the magnetic field is reversed. And this requires energy that can be felt as heat that reduces the efficiency of the motor. Now it gets technical because this energy consumed is called loss P, core loss, or iron loss. It can be approximated by the sum of three components: hysteresis losses, P hysteresis, eddy current losses, and additional losses or abnormal losses, but I will only speak about hysteresis and eddy current losses because these are influenced by material selection. Hysteresis losses can be visualized in a hysteresis curve. I'll place my electrical steel into the coil. Magnetic field strength H is found on the horizontal axis. I can control this by the strength and direction of the current. Flux density is found on the vertical axis, which is the number of magnetic field lines in the coil. Without current flow, the dipoles have no alignment in the electrical steel, and I have no magnetic effect toward the outside. The dipoles gradually align when the current is switched on, and the point at which all the dipoles are aligned is called magnetic saturation. This is the highest possible field gain. This initial alignment takes place along the so-called initial curve. Now I reduce the current. The point at which no current is flowing is when the field strength becomes zero, but not all dipoles will face in the same direction. Residual magnetization remains in the electrical steel strip, and this point is called remanence. Should the current now flow in the opposite direction, the direction of the magnetic field will change, and more dipoles will change their orientation. Magnetization in the electrical steel becomes weaker, and the magnetic effect of the dipoles toward the outside is completely eliminated as soon as a certain field strength has been reached. The magnetic flux density returns to zero. This is called coercive field strength. If I further increase the current, and thus the field strength, all the dipoles will align again at a certain point, and the material will again reach a point of magnetic saturation. But now the electrical steel is fully magnetized in the other direction. Reduce the current to zero, to remanence, then current in the other direction to coercive field strength, and then continue to saturation. The dipoles are always aligned along the outer loop and always follow the change in the direction of the current. This can be 50 times a second when the power comes from an electrical socket in the wall, but it can be a few hundred times higher than that, for example, in the traction motor of an electric car. And every time the polarity is reversed, energy is consumed to realign the dipoles and demagnetize the material again. The deciding value for this is the coercive field strength. The smaller it is, the narrower the hysteresis curve will be, and the smaller the area it covers. It also leads to lower hysteresis losses. The second relevant factor with respect to core loss is eddy currents. They explain why rotors and stators cannot simply be made of a steel block, but must consist of stacked laminations. Just as electric currents generate magnetic fields, alternating magnetic fields generate electric currents. As a general rule, eddy currents are formed in electrical conductors when the direction of the magnetic fields passing through this conductor changes. This happens naturally in our electrical steel when the direction of the magnetization changes. Within the material, these currents flow in closed loops. In a solid steel block, these eddy currents can be massive. In thin, electrically insulated lamination stacks, the eddy currents remain small and the loss is low. In the formula for eddy current loss, the frequency term is squared. The eddy current loss is typically proportional to the square of the frequency of the alternating magnetic field. This means that doubling the frequency will result in a four-fold increase in the eddy current loss. So the thickness of the material is of crucial importance, especially in the case of very fast rotating motors. Special alloys such as silicon, aluminum or manganese make a further contribution to the reduction of eddy current losses. These reduce the conductivity of the material, meaning that the current doesn't flow as easily and the eddy currents cannot become very big. Let's summarize. Core losses are caused by the constant reversal of polarity in electric machines. High-quality electrical steel strip can keep hysteresis and eddy current losses low. So that was an overview of the theoretical factors. But how do we reduce core losses and increase permeability, polarization, and flux density? Put simply, the answer is by optimizing the structure and composition of the electrical steel during production, as we do at voestalpine. Measures include proper use of alloys in the electrical steel and achieving the correct thickness. Special annealing processes are used to achieve optimum orientation and grain sizes in the crystalline steel grid. We avoid non-metallic inclusions and defects in the lattice structure. This means that our dipoles have less resistance when they are aligned. This all doesn't sound very spectacular, but it is a science that our specialists at voestalpine have mastered. Our isovac is one of the leading electrical steels on the market. If you want to know more about the amazing properties and possibilities of isovac electrical steel strip, please take a moment to browse our isovac website. Have fun browsing, and goodbye until the next steel tutorial.
voestalpine, one step ahead.